we're going to do some math. So we're going to look at the Hardy-Weinberg equations. There are two equations, and these are going to describe the alleles in a population, assuming that each individual has two alleles, and this population is going to be not evolving. So by not evolving, we mean that we can look at the alleles in one generation, and that's going to tell us exactly how many are in the next generation, because they're not changing. All right, so typically when we have alleles, we have a dominant allele, right, dominant, and we have a recessive allele. Those are our two options, and each individual either gets two dominants, two recessive, or one of each. So if we think about this, what we're going to do is assign some variables, P and Q. P is going to indicate the frequency of the dominant allele, and Q is going to indicate the frequency of the recessive allele. If these are our only options, big A or little a, there's no other options. When we add up all of the big A's and all of the little a's, that's going to be 100% of the alleles, right? That's all of them. So this is how we get our first equation. So a frequency is just how many there are out of the entire population. So a frequency we're going to write as a decimal. So P, the frequency of the dominant allele, plus Q, the frequency of the recessive allele, is going to be 1. 1 is the decimal version of 100%, right? So this is the entire population is represented by 1. That stands for 100%. All right, so here we can see, here's my population. And instead of sorting these into individuals, we've just got the alleles kind of floating around. These are the alleles for the snapdragons, the flowers. So our dominant allele P is CR for red, and our recessive allele Q is CW for white. If we just look at all of the alleles in the population, we can see that there's 80% red, so P is equal to 0.8. We can figure out P or Q if we have the other one, right? Because our equation is P plus Q equals 1. So if I know that P is 0.8, so 0.8 plus Q equals 1, can do some algebra, minus 0.8 minus 0.8. We end up with Q equals 1 minus 0.8. Q equals 0.2. And so this makes sense, right? So of our alleles over here, we actually have way few white alleles, and so that's going to be 0.2 or 20%. One thing that you can do to check your math, and I highly, highly recommend that you always double check your math, is, okay, I've got a value for P, and I just figured out a value for Q, so I'm just going to go back and make sure that 0.8 plus 0.2 does indeed actually equal 1, and it does. So I think I'm probably on the right track here. All right, but P and Q are the representative frequencies of each individual allele. We don't see individuals as alleles, right? We see them as phenotypes, right? So we have either the option of being CR, CR and being red, or CR, CW and being pink, or CW, CW and being white. So let's look at these. So CR, CR, that has two alleles represented by P. When we're looking with frequencies, if we have two of something, we're going to multiply them together, right? Multiplication. What's P times P? That's going to be P squared. So P squared is the frequency of this genotype. Or we can say this is the frequency of the homozygous dominant phenotype, right? Homozygous dominant. In this case, this is a red phenotype. All right, if you're pink, you have one allele for P and one allele for Q, right? Because dominant is P and recessive is Q. And we're going to multiply these together. P times Q. When we do the cross, this is actually twice as likely. We have two ways to get this. You can be CR-CW or CW-CR. So if you think about the Punnett square, where we cross CR-CW, CR-CW, there's 1, 2 spaces where we get CR-CW. So we're actually going to multiply this by 2. So that's how we get 2PQ. And this is going to be the expected frequency of the CR-CW genotype. In this case, we mean the heterozygote. For the snapdragons, this is going to be the pink phenotype. And then here we've got the last phenotype we can have, which is white, which is going to have CW. This is going to have a Q times Q, which gives us Q squared. And so these are our homozygous recessives. And for the snapdragons, this is going to be a white phenotype. So here's my second Hardy-Weinberg equation. Remember that the first one was just P plus Q equals 1. And here's my second one. P squared plus 2PQ plus Q squared equals 1. Those of you who've had algebra might think that this looks familiar. This is a quadratic equation. So we can actually derive these. Those of you who are interested in the math, keep watching. If you're not, you can skip ahead. So to get this from here, all I have to do is multiply these together. All right, so P plus Q times P plus Q is going to equal 1 times 1. Well, what does 1 times 1 equal? 1 times 1 equals 1. So I can just say that these are equal to 1. And then to get this last part, we're going to FOIL this, right? So FOIL, F-O-I-L, first, outside, inside, last. So the first is P times P, gives me P squared. Outside is P times Q, P, Q. Inside is another Q times P, so P, Q. And last is Q times Q, Q squared equals 1. These are the same variable, so I can add them together, and we end up with P squared plus 2PQ plus Q squared equals 1. All right, so let's take the allele frequencies that we had for our example where P was equal to 0.8. And from that, we figured out that Q was equal to 0.2. And we can plug them into these variables to figure out the frequency of the actual phenotypes, right? So these are going to be red, these are going to be pink, and these are going to be white. So P squared, we've got 0.8 times 0.8, which it's written out for you. I'm going to write it again. And so that is going to end up equaling 0.64, which is equal to 64% of the population should be red. 2PQ, 2 times 0.8 times 2, we end up with 32, or sorry, 0.32, which is going to be 32% of the population should be pink. And then Q squared, 0.2 times 0.2 equals 0.04. Be careful when you're multiplying that you multiply correctly. So when we change this to a percentage, we just move this decimal over twice, and that gives me 4% of my population should be white. And I like this drawing of the Punnett square here, and it's giving you kind of all of the possibilities, and each square size represents the relative amount of the phenotype in the population. So Hardy-Weinberg equilibrium is assuming that a population is not evolving. And this is not necessarily easy to do. So there are some conditions that we have to assume in order to use these Hardy-Weinberg equilibriums, to assume that something's in equilibrium. Most real populations are going to change over time, and they're not going to fulfill all of these conditions all of the time. So here are the 5 conditions for a population to be in equilibrium, which means that it is not evolving. So there has to be no mutation, absolutely 0 mistakes. Every time we do DNA replication, it comes out perfect. A large population. This means that the random chance of kind of losing one allele or just random fluctuations don't really affect the population. We're looking for something really big. 10 individuals is not a large population. No gene flow. Gene flow is the movement of alleles either into, so immigration, or out of, emigration of a population. So no gene flow means that all of the individuals in the population are staying in the population, and no new individuals are coming into the population. Maybe they built a wall. Natural selection, so no natural selection. What this means is that all of the alleles are equally successful. So the P and the Q alleles are both going to be the same amount of adaptive. Neither one is going to be selected for over the other. And then random mating. Random mating means that each individual has the same chance to be selected as a mate as any other individual. So what this would mean in your life is that any person that you could mate with, so of the opposite sex, in your population is the equal chance of being your mate. And that's highly unrealistic because we choose mates based on a lot of things. So if you think about any population that you're aware of and go through all of these 5 conditions, it's probably not likely that they're not evolving. However, sometimes we can assume Hardy-Weinberg equilibrium for a specific gene because it might fulfill these conditions at one time.